Hello and welcome back. If you're joining me for the first time, I'm glad you're here. Tonight, we're going to stay calm, stay precise, and follow the data where it leads. Because out in the dark, there's a rare visitor moving through our solar system, and the newest observations suggest it isn't behaving as simply as gravity would predict. So settle in, take a breath, and let's start with what we actually know. When NASA calls an object interstellar, it is not poetry, it is geometry. Tonight, I want to slow down and stay close to the evidence because 3IATLAS has done something that forces the data team to blink and then recalculate. The path is still hyperbolic. The visitor is still leaving, but the details we use to predict its future motion have shifted again. For most objects, it does. Gravity dominates. The trajectory tightens with each new measurement, uncertainty shrinking like a knot being pulled closed. But this one does not behave like a clean gravitational problem. Over the last set of observations, the solution has had to be revised, not because the telescopes failed, but because the object itself appears to be adding a faint extra push. A non-gravitational drift, the kind you only get when sunlight heats an icy surface and gas escapes fast enough to act like thrust. In other words, it is not simply falling through the solar system, it is reacting to it. That is the tension I want to explore with you. So in this video, I will walk through what an orbit update actually means, how outgassing turns into measurable acceleration, why a rotating thrust vector can make predictions drift, and what the newest images hint at when you treat them not as pretty astronomy, but as evidence. The new orbit is still an orbit, but it is no longer just gravity. An orbit solution is not a single track carved into space. It is a best fit, a living answer to a moving question. Every new measurement of position, every astrometric dot from a survey telescope tightens the fit. And for most asteroids, gravity does almost all the work. But comets are different because they leak. Their momentum changes not by impact, but by evaporation. In practice, orbit solvers treat that extra push with a standard framework that has been used for decades on active comets, the Marsden non-gravitational parameters, usually written as A1, A2, and A3. They represent an extra acceleration component in the radial direction, the transverse direction, and the normal direction relative to the comet's orbital frame. When those terms are statistically significant, it means the comet is not just falling. It is also thrusting gently in a direction that depends on where the vents are and how the nucleus is oriented. One recent analysis that pulls its orbital constraints from JPL horizons reports significant radial and transverse components with A1 and A2 on the order of tens to hundreds of 10 to the -8 astronomical units per day squared, implying a net non-gravitational acceleration near perihelion on the order of about 10 to the -7 meters per second squared. That number sounds microscopic, and it is. But microscopic is not meaningless when you apply it continuously to an object racing through the inner solar system. This is why the orbit has to be updated. Because the engine is not constant. Outgassing is not a flare, it is a rotating force vector. Here is the part that can feel unintuitive. When we say the thrust vector changed, we are not imagining a single nozzle that swings like a steering wheel. Most comet activity is messy. It is patchy. It comes from multiple vents. It turns on and off with local sunrise, with shading, with the depth of volatile layers beneath the surface. If a nucleus rotates a jet that is fixed on the surface, sweeps through space like a lighthouse beam. If the active region evolves, or a new patch opens the average directions of thrust shifts. And if the volatile species driving the jet changes the timing of that thrust changes too. NASA's overview emphasizes that 3IATLAS remained visible through September, then was unobservable near the Sun, then returned for early December observations. That gap matters because perihelion heating is where the interior begins to respond with delay. Thermal waves do not instantly penetrate. They creep. That delayed response is exactly why observers watch comets closely after perihelion. Some of the most dramatic changes occur when the surface looks like it should be cooling, but deeper layers are finally waking up. That is how you get a moving target in the mathematics. A comet's thrust is not just on. It is shaped by rotation, by geometry, and by time. The coma is telling us the thrust is not symmetric. If I want to know whether thrust is changing, I do not start with equations. I start with shape. NASA reports that Hubble imaged 3IATLAS on July 21, 2025, and revealed a teardrop-shaped cocoon of dust streaming from the solid, icy nucleus. A teardrop is not a perfect sphere. It is a direction. It is the sky writing down a history of emission. As the comet approached and then passed perihelion, the coma and tail did what active comets do. They evolved under sunlight radiation pressure and the solar wind. Space-based and ground-based campaigns have been coordinated across an unusually wide network, including Hubble and spacecraft assets, precisely because these details are how we infer composition and dynamics. In late November, Gemini North observations reported by Live Science describe a coma that grew brighter and took on a stronger greenish hue, with diatomic carbon cited as a likely contributor to that emission based on a NORLAB statement. Color shifts like that do not automatically mean the comet is changing identity. They can mean the observing geometry changed, they can mean the dust properties changed, or they can mean new gases are becoming dominant as different layers sublimate. But in the context of orbit updates, the important point is simpler, new molecules and new dust streams imply new mass loss patterns. New mass loss patterns imply a new recoil pattern. A new recoil pattern means the best fit orbit must be recalculated, not because gravity stopped working, but because it is no longer alone. And there are hints of structure beyond a single smooth tail. Reports discuss multiple tails in imagery and sun-facing jet activity in this interstellar comet. Jets are not decoration. Jets are force. Interstellar speed makes small forces add up faster than you expect. Now I want to widen the frame. An interstellar object is already defined by its trajectory. NASA explicitly notes that the orbital path is hyperbolic and does not follow a closed loop around the Sun, and that tracing it backward places its origin outside our solar system. That geometry comes with speed. This object is not meandering in a long ellipse like a typical long-period comet making a slow return. It is passing through on a one-time corridor. In that regime, even small accelerations matter because the encounter window is short and the observational cadence is dense. Orbit solvers are constantly integrating new measurements, and each new day of high-quality astrometry can reveal whether the residuals prefer a purely gravitational model or a model with recoil forces included. One ArcSIF analysis describes exactly that logic. The non-gravitational solution reduces systematic residual trends compared to gravity only fits consistent with recoil forces from anisotropic outgassing. This is not an exotic claim. It is the standard language of comet dynamics. But when it happens to an interstellar visitor, it feels louder because everything about the object is already rare. Why Orbit Update is really a story about uncertainty. Shrinking. When you hear updated orbit solution, it can sound like a reversal, like yesterday's path was wrong. That is not quite what it is. It is closer to how weather forecasting works. The atmosphere obeys physics, but you only know its state imperfectly. You refine the state with new observations. The forecast changes because the uncertainty map changes. For 3IATLAS, the observation network is immense. NASA's page lists assets ranging from Hubble and Webb to Mars orbiters and even heliophysics missions that can glimpse the comet near the Sun. Space.com reports that ESA's JUICE spacecraft targeted 3IATLAS in early November, but that the high-resolution dataset will not reach Earth until February 2026, with an early preview obtained through a lower-rate communications trickle. This is where the orbit can tighten again, not just because JUICE sees the comet, but because spacecraft-based astrometry can be geometrically powerful. It changes the triangulation. It reduces degeneracies. It can separate apparent motion from small accelerations that mimic motion. So if you are watching the orbit update day by day, what you are really watching is a contest between two explanations for the same residuals. Option 1, we measured wrong. Option 2, the comet pushed itself. In active comets, option 2 is often the correct one. What the chemistry hints at and what it does not. Let me be careful here. Unusual chemistry does not automatically imply an unusual origin story beyond formed around another star. Interstellar alone is already unusual. But chemistry does help constrain how outgassing behaves, because different volatiles turn on at different temperatures. Carbon monoxide can drive activity farther from the sun than water ice. Carbon dioxide can dominate in intermediate regimes. Water becomes powerful closer in. Space.com reports that a NASA-led campaign has hinted at unusual chemistry in the dust, including discussion of a higher than normal carbon dioxide to water ratio and gas unusually rich in nickel relative to iron, presented as part of a NASA news briefing. Live Science covering Gemini observations frames the green coma as consistent with diatomic carbon emission and notes that 3IATLAS appeared redder earlier in the season, suggesting changing release of molecules as heating progressed. These are exactly the kinds of clues that tell me the thrust environment is not stable. If the dominant gas changes the momentum, flux changes. If the active areas migrate, the direction changes. If the dust grain sizes shift, the coma shape changes, and the coupling between gas and dust changes. And if you want a reason why the orbit needs updating, that is it, evolving mass loss. The debate is real, but the physics does not need drama to be tense. Whenever an interstellar object appears, people rush to label it natural, artificial, harmless, dangerous. But I think the more unsettling possibility is simpler. What if we have been using the wrong frame entirely? Because if 3IATLAS is showing repeated changes in its thrust direction, then it is not merely experiencing outgassing. It is choosing a course the way a spacecraft chooses a burn. In that case, the orbit solution is not a prediction. It is a negotiation between us and something that is actively rewriting its own future. And if NASA is issuing updates, it is because they can see that negotiation happening in the residuals. I want to be clear about what this would mean. A hyperbolic orbit is often described as a one-time pass. But if the thrust is strong enough, a hyperbola can become an ellipse again. That means 3IATLAS could remain bound, even return if the object continues to accelerate itself in the right direction for long enough. So the real tension is not whether it is interstellar. The tension is whether it decides to stay. The images do not answer that directly, but the chemistry might. A gas rich in nickel compared to iron does not fit the clean expectation for ordinary cometry material. If nickel is rising while water is falling, then I have to at least consider a disturbing possibility. We are not seeing a normal volatile transition. We are seeing exhaust, and exhaust has intent built into it. The orbit update means we no longer know where it will be tomorrow. This is the part people misunderstand. When the orbit solution updates, the public hears refinement. But what it actually means is that we were wrong yesterday, and we might be wrong again tomorrow. If the thrust vector rotates again, the object will not be where gravity says it should be. It will be where its own engine says it should be, and the distance matters. An astronomical unit sounds vast, but in the language of orbital uncertainty, it is not a guarantee. A change of only a few arc-seconds in position can translate into millions of kilometers of uncertainty months later. So if you are thinking of 1.8 astronomical units as a stable buffer, you are thinking in human terms, not in dynamical terms. The object could come closer than expected without warning, not because it turns sharply like a plane, but because small pushes early create large divergences later. In chaotic regimes, tiny accelerations do not stay tiny. They scale. So the updated orbit is not just an update. It is a signal that the system has become unpredictable. The coma is not just a cloud. it is a control surface. Most comets have comae that look like soft halos, but 3IATLAS has shown a skew, a tilt, a teardrop. And if that teardrop is persistent, it implies the object is shaping its own flow in a consistent directional way. I want to push this further because the geometry is too convenient. If a nucleus rotates, jets should smear into patterns that average out. The coma should become more symmetric over time unless the rotation is being stabilized or corrected. A stabilized rotation means the object is maintaining a preferred orientation. A preferred orientation means torque control, and torque control is not something we casually assign to a dirty snowball. This is why the debate will not die down, not because people crave drama, because the observations keep handing us asymmetry, and asymmetry in dynamics is a fingerprint. What happens if the thrust keeps rotating? If the thrust direction continues to swing, then I expect the next orbit solution will shift again. But more than that, I expect the nature of the shift will change. First, it will look like a gentle drift. Then it will look like a curve that does not fit any standard comet model. Then it will force a reclassification. At that stage, the question will no longer be, what is the comet made of? The question will be, what is it doing? Because outgassing is an explanation you can subtract. Once you subtract it, whatever remains is the part you cannot hide behind sunlight and ice. And if something remains, then this was never only a visitor passing through. It was a probe of our predictive limits. So tonight I am not ending with certainty. I'm ending with a test. In the next video, I'm going to take the newest images and treat them like telemetry. I will map the coma skew as a vector track, how that vector rotates night by night, and compare it to the direction the orbit residuals demand. If those two vectors line up, it means the coma is literally marking the direction of thrust. And if the thrust direction aligns too cleanly, too efficiently, then we have to face the most uncomfortable possibility of all, that 3IATLAS is not merely responding to the sun. It is responding to us noticing it. Because the moment we started measuring it, the orbit began to move. And if it shifts again soon, not as a drift, but as a deliberate correction, then the next orbit update will not feel like science. It will feel like contact. And that is where I will pick up next.